This is segment 2 of our review session 4 for 4th exam, Chem 112. I'll begin with nuclear transmutation. Radioactive elements suggest a spontaneous nuclear reaction. On the other hand, you may have non-spontaneous reaction, which is often man-made, and we can do those things in the lab. We call it nuclear transmutation. So these are non-spontaneous reactions. I'll give you one example. When you react nitrogen with alpha particle, this is helium-24 is same as alpha particle, temporarily you are going to get fluorine 9, and on the top you'd have 18. Now what you need to do is add up these bottom numbers, that gives you 9, and atomic number 9 is fluorine. Make sure you have a periodic table with you. 14 plus 4, that's 18. That's the mass of fluorine. What happens is, in this reaction, you have 7 protons. 1, 2, 3, 4, 5, 6, 7 protons. I'm ignoring neutron for the time being. And you're colliding it with helium with 2 protons. So this is 7 protons, 2 protons. From physics, we know that whenever you bring these 2 positive charges close to each other, there'll be repulsive force. As you get closer and closer, repulsive force gets greater and greater. So in order to fuse them together, the amount of energy that is needed would be very large. So in other words, for this reaction, we'll have to energize these particles. So that would be our next topic, what we call particle accelerators. So let me first give you the final product here. Now, once helium goes into nitrogen, it has to have enough energy so that it can get into this nucleus. Since it would have lots of energy, and that would eventually break up this intermediate atom, and it would finally give oxygen 817 plus a proton. So this is the final product of this particular nuclear transmutation reaction. Now, from this example, we know that we had to energize helium or alpha particle, and this is done by using cyclotron or synchrotron. Cyclotron is the older device, and the synchrotron is the most modern advancement and modification of cyclotron. So let me go over cyclotron first so that you would have an idea what is done in synchrotron. So it basically, there are 2 D-shaped electrodes. This is hollow. So these are D-shaped electrodes. Say for the time being, this is negatively charged, this is positively charged. Obviously, you'll have to have some kind of voltaic cell so that it would be negative here and positive here. Allow alpha particle to enter into this through, so this is the hole here. So you allow alpha particle to go through here. So that's plus 2, or alpha particle. Now, whole thing is bathed in magnetic field. So let me write down the key components. Magnetic field. Magnetic field is a force of attraction that you get because of the presence of magnet. So this whole thing is bathed in magnetic field. So if this is a D, you would have a magnet at the bottom and top, so that the magnetic field will be going perpendicular to this. Now, one property we know from physics is if there is a moving charged particle and there is a magnetic field, the path of the particle is going to be bent. So in other words, even though I have my alpha particles within this D, is going to be bent like this because of this magnetic field. Now, as soon as it comes out, this is the positive, is now facing negative. So there is an attractive force. And from physics we know that when there is an attractive force, there will be an acceleration. Think about, I'm holding this pen, and there is an attractive force due to the gravity is pulling downward. If I let it go, it would not only go down, it would also accelerate or energize. So each time you move towards source of attraction, is energized. You'll be energized because your velocity will keep on increasing. Same thing is true here. The positive charge, as soon as it comes here, it sees the negative here. So it will be accelerated from this location to this location. As soon as it enters into this D, again this is shielded from the charge, now but it will face the magnetic field. So it's going to be, again, path will be bent. Again it comes here, then it sees the negative charge. So this positive and negative are changed in such a way that at the time when the particle comes here, it sees the negative. When the particle comes back here, it says negative again. So now it will be accelerated here. So this is how it goes around and gets accelerated. So what magnetic field does here, it bends the path of the particle. What about electric field? Electric field is due to this positive and negative in this electrode. And these are all regulated externally so that this can be switched back and forth depending upon where this positive charge is in this D. So electric field would be energizing the particle. In the gap, the particles are accelerated or energized. So that's about cyclotron. This is one of the earliest devices for accelerating or energizing particles before doing transmutation reaction. Recent version is synchrotron. Now in synchrotron, what we do, we don't want these energized particles to move in a larger and larger circle. We keep it at the same radial distance. So in other words, in order to do so, the magnetic field cannot be constant. So unlike cyclotron, magnetic field strength is changed, is increased as particle gets energized. I can give you an expression for this. Force is given by QV times. This is the magnetic field, this is the charge, this is the velocity. So this is the force that keeps the moving object in a circular motion. So if I want to keep it at the same radial distance, the B has to be increased as particle gets energized. In other words, we can say that in synchrotron, magnetic field is changed. And in most recent synchrotrons, both magnetic field as well as electric field is changed or varied with time. That's how you can get a most efficient particle accelerator. The key thing to know for your exam would be what is the function of electric field, what is the function of magnetic field in accelerating particles. Next, we are going to show you the devices used for detecting radioactivity. So this is our practice number 6, problem 6. So practice number 6. I could be wrong with my numbers, but I just want to make sure this is a practice problem on radioactivity. Now, the detection of radioactivity. Most popular detection device is Geiger-Müller counter. In your book, this says quite often this is a Geiger counter. Now this is how Geiger counter works. You have an anode inside. This is anode. And this is a cathode. So this anode is kept positive. And the cathode, the container itself acts as a cathode, as negative. And then you apply a voltage here. So you have an anode, cathode, and argon gas. Now this serves as a detector of radioactivity. Now how? Let's assume that alpha particle gets inside. It could be alpha particle, it could be beta, it could be gamma. Any of these energetic radiation would knock off electron from argon. So basically, argon is going to lose electron. So these radioactive substances, what are the substances that come out of a radioactive element, they would knock off electron from argon. So you'd have argon plus and E minus. So argon plus E minus. So there will be lots of those. And whenever you have these ions, there will be conductivity, because argon will be attracted towards negative plate, electron will be attracted towards the positive plate. So there will be flow of electricity, and that would show up as a signal. So keep that in mind, and there will be a signal. So, and each time there is a signal, they would multiply that signal, and that would tell us that there is some kind of radioactive substance got inside. So each event of ionization would be counted in Geiger counter. And it's a very common counter in recent days. There are other kinds of counters too. We call it scintillation counter. In scintillation counter, you'd have a zinc sulfide plate. When a radioactive substance strikes this plate, it gives light. Again, your detection is based on how much, what the light, comes out of here. So each time a light is detected, light is detected, that means scientists would know that you have some kind of radioactive element striking the zinc sulfide plate. So this is called scintillation counter. So scintillation counter is based on emission of light, and that's being detected and amplified to know the event of caused by radioactive substance. So in this case, radioactive substance causes ionization. In this case, emission of light. So you need to know how these different detectors are different. You also need to know the difference between fission reaction and fusion reaction. So some of these differences you need to know. Let's call it 7. Fission and fusion. Fission means I have a radioactive element. If it's broken down into two big chunks of masses, this is one, doesn't have to be equal. These big chunks of masses, that is called fission. On the other hand, I have a radioactive substance, only tiny bit broke down out of that. So if I have something like this, only tiny bit come out of it, it's not a fission reaction. So in other words, in order to be a fission reaction, each of these masses that comes out of after breaking of this nucleus each of this fragment has to have significant mass, not a tiny mass like 2, 3, 4. Those are small masses. I'll give you examples so that you understand which one's a fission reaction, which one's a fusion reaction. In exam, I'll give you reactions like those, so make sure you can recognize the right one. Let me write down this equation so that we can explain this to you. Uranium 92, 238. Neutron, you don't need to energize neutron because it's neutral. It can get into any nucleus. It would not be repelled by a nuclear charge. So it goes inside, and finally it would break down into tellurium 52, 137, zirconium 40, 90, plus 2 neutron. Okay? Make sure the bottom numbers add up, should be equal to 52 plus 40 plus 0. And top number will be, in this case, 2. 2 times 1, 2, plus 90 plus 137. And this will be 238 plus 1, 239. So bottom numbers needs to be balanced in nuclear reaction. Top numbers need to be balanced too. Now the question is, what kind of reaction is this? Did we get two big chunks of masses? Obviously, uranium broke down into tellurium and zirconium, and 2 neutrons came out. Yes, these are big chunks of masses. One has the mass 137, the other one is 90. So yes, this is a fission reaction. In this case, fission is caused by neutron. In most cases, it's the neutron that does it. You have a slow neutron that goes inside, transfers its energy, and then finally breaks up the whole atom or nucleus. Let me show you another one. Alpha or helium 24 plus uranium 92, 238. The only difference is in the last example we have neutron, here we have helium or alpha. It's the same as helium 24. Okay? And product is plutonium 94, 241 plus neutron. You don't need to memorize this, but what you need to know is what type of reaction is this? Is it a fission reaction? It broke down into uranium, broke down or changed into plutonium, and 1 neutron came out of it. Answer is no, because this product has a very small mass. So this is the only mass you have. The other mass is negligibly small, very small. It's not a significant mass. So not a fission reaction. By small mass, I mean mass 1, 2, 3, 4, 5, 6. Those are pretty small masses. Gives it 25, 30, 40. Those are the big masses. Now, this is all about fission reaction and not fission reaction, but breaking down of nucleus. So by breakdown of nucleus doesn't always give you fission reaction. Now let's go over fusion reaction. Fusion is just the opposite of fission in the sense that you have lighter nucleus, you bring them together, and finally fuse them together. As I mentioned, fusion requires loss of energy because they repel each other before you bring them close. So those particles need to be energized by using cyclotron or synchrotron. One of those particle accelerators need to be used. So once you use those particle accelerators, then you can combine them. So let me show you one of them. 2 hydrogen, and we get this second kind of hydrogen called deuterium. It is also hydrogen but heavier, 2 times heavier than the regular or most abundant hydrogen. Plus, this is not electron, this is positron, positively charged electron. So always double check. 1 plus 1, 2 on the left hand side. This is 1 and 2. On the top also is 2 and 0 makes 2. This is the fusion reaction. I'm bringing those two hydrogens and fuse them together to give this product. So combining lighter nuclei to one larger one is called a fusion reaction. So you'll have to know the distinction between fission and fusion reaction. In this exam, there would also be questions, what we call descriptive chemistry. That means there is no math involved in those, but you need to know the information. There will not be too many questions like this, but there are a few questions like those. Because I think that by taking Chem 112, you need to know questions like those, the answers to those questions. Like in my lecture note, you'd find this information in book. Of course, you have to. The information that you find in my lecture note, which is posted in Angel, should be enough for your exam. Polymers. I may ask you about what makes a polymer. What is condensation polymer? Condensation polymer. What is cross-linking? How does it affect rigidity of a polymer when you cross-link? Cross-link, basically you have all these polymer long chains. You cross-link with often sulfur. That gives you rigidity. And condensation means the reaction where water comes out, especially in case of polymer reaction. Among different polymers, we often talk about most commonly known polymers like starch, for example. The starch is a polymer of glucose. Similarly, glycogen, cellulose, these are all polymers. Our paper is made up of cellulose. Again, if you break it down, eventually you get glucose units or sugar units. Then you need to know ceramics, composition of ceramics, like silicates, carbides, oxides. So again, my lecture note has all this information. And then you need to know liquid crystals. So you need to know about different types of liquid crystals, what can change their orientation, whether electric field has any effect on the orientation of these molecules. You need to know that. Then you need to know about superconductors. Basically, you need to know what makes a compound a superconductor. So, loss of electrical resistance. Normally, when that electricity is flow of electrons, as the electron flows through any cable, that electron bumps all over and loses energy. Because of the resistance, there will be some heat production. That's not the case with superconductors. Superconductors would go through without any resistance. Okay, so superconductors, no resistance at all. So that's why scientists are trying so hard to get room temperature superconductors. There are some superconductors which now work at a much higher temperature than what scientists had earlier. But still, they're not usable at this point because most of them are brittle, so scientists are trying something that could be used. When we discuss about superconductors, we need to know what is Meissner effect. Every superconducting substance would show Meissner effect. What is Meissner effect? Say this is superconductor. And I have a magnet This is magnet. Magnet is going to float as if there is no gravity acting on the magnet. And that Meissner effect. So in books you'd see this kind of definition that it excludes magnetic field. It excludes magnetic field means it repels a magnet, so that it's going to float. So that's why scientists are thinking about using magnetic train that would be highly efficient if there is a superconducting substance discovered, which would be quite efficient at room temperature. Then those magnetic trains would be less expensive too. So that's Meissner effect. So superconductor would exclude magnetic fields. Then you need to know what we call biomaterials. Again, these are part of descriptive chemistry. Biomaterials. Now again, my lecture note should be sufficient because we mentioned there what are biomaterials, their physical and chemical requirements. Keep in mind, a lot of these biomaterials are used inside our body. So it should have some chemical stabilities as well as physical strength. It should not break down when it's implanted in our body. So you know about biomaterials, their physical requirements and the chemical requirements to be an effective biomaterial. Now we're going to do a problem. Let's call it problem number 9. Now I'm going to write down this question first. The question is how much energy is released in this nuclear reaction. How much energy is released? So I'm going to first write down the reaction. Plus helium-2-3 giving helium-2-4 plus now if I give you a reaction like this, I must give you the masses. So you have to read carefully whether those are atomic masses or nuclear masses. Most of these problems would have atomic masses. Atomic masses means that has electron in addition to the protons and neutrons. So I'm copying these numbers from the book, which is for this is 2.01410 atomic mass unit, AMU. For helium 3 is 3.01603 AMU, and for this helium 4.00260 AMU, and then for hydrogen it's going to be 1.00782 AMU. Keep in mind this is the atomic mass but not nuclear mass. Before I do find out this energy, how much energy is released. Now, when the question is asked how much energy is released, you must think what expression to use. Here, there will be loss of mass. Always, in all nuclear reactions, that's how you get energy. Product would have a smaller mass than reactant. That means, with a bigger mass, when you get a smaller mass, a part of the mass disappears. We call it mass defect, because that mass is changed to energy. So how do I get that energy? Delta M C squared. That's Einstein's expression. This is the mass that decreased as you go from reactant to product. This is unlike chemical reaction. In a chemical reaction, there is no change in mass. In a nuclear reaction, there is change in mass. As you go from reactant to product, the mass is decreased, and that is changed to energy. That's how we get energy from a nuclear reaction. So let's figure out it here. These are atomic masses, so I must subtract electron mass. So minus electron mass. So you have to get that value from the book. I got this value from the book. Now it has 1 electron. So let's write down here. 1 electron here, 2 electron here, because 2 protons must have 2 electron. Here you have 2 electron, because I have 2 protons, and 1 electron. So I must accordingly subtract. 1 electron mass is 5.485799 and times 10 to the negative 4. 10 to the negative 4 AMU. Second case, there are 2 such electrons, 2 times 5.485799 times 10 to the negative 4. And third case, minus, again, there are 2 such electrons, 2 times mass of electron, 5.485799 AMU. And in the fourth case, that's the only 1 electron here, so minus 5.485799 AMU. So once you subtract that, make sure you have all these significant figures, otherwise your values will be way off. I'm just going to show you one of these values. This is for this one, 2.01355. That's what I got. But make sure you double check that independently. This is the problem from the book that I have selected. I think it's chapter 21, 50C. In the same way, find this value, and this value. Then how do I get delta M, or mass defect? Delta M would be then by product value added together. So nuclear masses. So this is the nuclear masses. Let me write down here. Nuclear mass. So you'll have to get nuclear masses after subtraction. But because you have electron together with the nucleus. So subtract the mass of the electron. So now I get a mass of nucleus, and this is the mass of the nucleus. So after you do all this subtraction, then do the following. The product values added together. Helium-2, 4. So that's the masses. So mass of helium-2, 4 plus mass of hydrogen, that's products, minus reactant masses, doublet mass, helium-2, 3. After you subtract, these are the nuclear masses. Don't forget that these are nuclear masses. Then you get this value. Once you get the nuclear mass, let me remind you here, this is nuclear mass. So after you get the nuclear mass, that would be AMU. So I'm assuming that after subtracting these, you get this value here, times c squared, that's the velocity for light squared. 3.00 times 10 to the power 8 meter per second. This would be squared. Now, energy unit would be in joule. So in this particular case, in order to get joule, you must have the following. Let me write down here. Joule is kilogram meter square per second square. This is going to give me meter square per second square, but I must change AMU to kilogram. Let me show you how we can do that. And for that I need a little more space. So let me make some space here. So from here, you can get atomic mass unit times 6.022 times 10 to the power 23. That's AMU. That makes the gram. This is the conversion value. Same as Avogadro's number. That makes 1 gram. 1,000 gram makes a kilogram. So now once you got this kilogram from AMU, then you can use this, C squared. I suggest that you do it independently for your practice, and that would give you joule per atom. Because if you look at the reaction, it's 1 atom of hydrogen reacting with helium, giving you helium-4 and hydrogen-1. So if you want to get it in per mole, from atom to per mole, it would be 6.022 times 10 to the power 23 atoms. Atoms, or you can say nucleus, that many nucleus or nuclei per mole. So basically, Avogadro, you can save your time. Here Avogadro's number is on the top, here Avogadro's number is on the bottom, so you can cancel out and you can get your final answer in joule per mole. So make sure you try this and be careful with the units. Let me repeat this. From given atomic masses, you first get nuclear masses by subtracting mass of electron. Once you get nuclear masses, then add up product masses, product nuclear masses, minus the reactant nuclear masses. And your answer will be in atomic mass unit, so you get this number. Atomic mass unit is not the right unit for calculating joule, because you need to have kilogram in presence of, instead of AMU, and then it has to be multiplied by meter squared per second squared. Meter squared per second squared is coming from velocity of light squared. So we're going to use that, and this is the conversion from AMU to kilogram. So, and then you get joule per nuclear particle, or say per atom, and then you change it per mole. And this is the final answer, because this question is asked how much energy is released per mole. If I don't use the word per mole, then you don't need to multiply this by Avogadro's number at the end. But most of the time we ask for energy per mole.